senior figure, the Rothschild professor for that program. And on the occasion of the Mathematics for Planet Earth program, we have the privilege to have David Ruelle from IHES in Paris. For me, somebody of my generation, David Ruelle has been a figure that has been in my academic life since ever I can remember, from early papers. Not his most famous papers, but some papers that I remember about turbulence and so on were very influential when I was growing up, as it were. So it's been a real pleasure to have him here. He's infinitely distinguished and famous for many different contributions in dynamical systems, ergodic theory, as I said, the theory of turbulence, statistical mechanics, and so on. And I don't need to say anymore. I'll just introduce David, who's going to give his talk on non-equilibrium from heat transport to turbulence to life.
Thank you. Cambridge is a high place of world culture, and it's a pleasure to be here again. Many of you would agree that doing science should not be one's only occupation in life. And perhaps many of you will also agree that if you are interested in science, it's advantageous to study something that is interesting. From this point of view, mathematical physics is a good subject because it has this miraculous aspect that it relates to things which in principle have nothing to do with each other, the logics of mathematics and the nature of the physical universe. So at least I'm not the only person who noticed that. There's a famous paper by Wigner on on precisely this question, but one might say that Newton had also discovered this fact that there is interesting mathematics combined with interesting physics in a way that one could not guess. That's a miracle, sort of miracle taking place. Okay, so that's more or less how I got into mathematical physics. And however, it doesn't mean that every time you try to combine physics and mathematics, you do something interesting. I had the luck of getting interested early in life in equilibrium statistical mechanics. Now, equilibrium statistical mechanics sounds like mechanical engineering or something like this. The point is that it does lead to very interesting mathematics. That's not completely obvious, but if you study it, you can't fail noticing that there is this underlying deep and interesting mathematical structure lying below so-called equilibrium statistical mechanics. I was much less certain about non-equilibrium statistical mechanics, because non-equilibrium is everything. I mean, everything that is not in equilibrium is in non-equilibrium. So the subject is too vast, and for a long time I thought there was nothing very interesting to be done there. I knew that my colleague Joe Leibowitz was working there, but I was not convinced. And it's only when Giovanni Gallavotti explained to me his ideas about the subject that I realized that there is underlying mathematics that is natural and very interesting. And the underlying mathematics is basically the theory of general smooth dynamical systems, of which I knew a little bit, and which is mathematically a very difficult but interesting subject. So I try to go into that, starting about classical statistical mechanics. Quantum I forget. For some reason, classical is more natural from a mathematical point of view. At least it's easier. Now, to understand non-equilibrium, it's good to have some idea about equilibrium as well. And what is equilibrium? It's an emergent theory from Hamiltonian mechanics. You forget about the dynamics. You introduce some new notions like the entropy, and it turns out that you have a very natural mathematical structure that I cannot go into here, but basically it's the study of certain states or probability measures called equilibrium measures that describe certain states of systems that you find in nature. And these probability measures have the form of e to the minus energy over kT times a volume element divided by a normalization factor. If you know it, you recognize. If you don't know it, well, it's not possible to go into more detail. Non-equilibrium is a program rather than a theory. People agree that there is entropy creation, although entropy is not defined in general. And this is a situation where instead of having a Hamiltonian, like in equilibrium statistical mechanics, either you have an infinite system or you have non-gradient forces. Now, at this point, I must say that people disagree as to what non-equilibrium is, and I shall impose upon you for this, for the duration of this talk, some of the possible ideas. Some people think that non-equilibrium is stochastic differential equations. I don't agree, and I will propose to you some other ideas. The ideas which were told to me by Galavotti at first time was that you start with a finite system, non-gradient force, but then the system tends to heat up, so you have to introduce a thermostat, and it's possible to introduce a so-called isokinetic thermostat that does not force you to consider infinite system. So having done that, then you can study non-equilibrium close to equilibrium, where there is this linear response formula, Green-Kubo, etc. And here you are in a domain where you use the time evolution even inside the equilibrium domain. Now, let me say something about this linear response without assuming that you are close to equilibrium. So I assume that I have a non-equilibrium steady state. That is not necessarily the only necessary approach, but it works well. It gives a nice framework for the study of non-equilibrium. So you start with a time evolution, which is given there, and a non-equilibrium steady state, which I'll describe more precisely in a moment, and then formal first order calculation gives a change in the expectation value of an observable when you make a perturbation, which you may take independent of time. And in general, this gives you quantity, which is the response of the system to a periodic perturbation. This is called the susceptibility. In equilibrium, the non-equilibrium steady state, so if you perturb close to equilibrium, your non-equilibrium steady state is in fact equilibrium, and you assume that it has a density with respect to the bag, then this the previous formula can be integrated by parts, and you get the Green-Kubo formula, which leads to the so-called fluctuation dissipation theorem. Okay. Now, to proceed with study of linear response, it is nice to assume that you have a system that is hyperbolic. Namely, there are these directions where where the dynamic expands and others where it contracts, so-called stable and unstable directions. And the susceptibility can be written formally as a sum of two terms where you have put the perturbation x to be the sum of a stable contracting and an unstable expanding direction. Now, there is a problem that I can only discuss very briefly, which is that for these hyperbolic systems with a stretching and contracting direction, usually there is an infinite number of invariant states under time evolution, and we would like to have just one that we would call non-equilibrium steady state. And the idea is to start with something like Lebesgue, which has a smooth density, to let the time evolution act on it, and then you get these so-called SRB state, which preserve some smoothness along the expanding direction, but then become singular distributions in the transverse direction. Now, this formal linear response theory leads you to think that you have the Fourier, since you have an integral from 0 to infinity, one-sided Fourier transform, it is natural to think that this one-sided Fourier transform will extend to an analytic function in the upper half plane. This is this corresponds to so-called dispersion relations, and we heard a talk by Viviane Baladi earlier, which says that this is not always the case, that it extends to analytically to the upper half plane. On the other hand, in practice, it may be a good idea, and in fact, Valerio Lucarini has used this idea in the study of perturbations of steady state corresponding to the climate. Okay, so there are rigorous, I spoke of the formal linear response, one can prove actually theorems if one uses so-called hyperbolic diffeomorphisms and flows. Those are for which the stretching and the contracting direction exist, span the whole space, and depend continuously on the point where you are. And an example is the geodesic flow on a manifold of negative curvature. So if you have a compact manifold of negative curvature and you look at the unit tangent space, the space of unit vectors tangent to the manifold, is a 2n-1 manifold on which there is a natural time evolution which is defined, which is the geodesic flow, and which has the nice property that it is hyperbolic. It's a so-called Anosov flow. It is also a Hamiltonian system. So it would be a good case to study non-equilibrium close to equilibrium. Now, the case of unimodal maps show examples where there is a breakdown of the dispersion relations. Now, all these things have been studied in great details by a number of people. I mentioned certain names, and there are many more, and a lot of work has been done on that. So that was my brief introduction to non-equilibrium. As you see, I have sort of reduced the study of non-equilibrium to the study of dynamical systems, or more precisely, of hyperbolic dynamical systems. Now, it's a fact that not all systems that one encounters in nature are uniformly hyperbolic. Some may be. Many results that one obtains for uniformly hyperbolic dynamical systems seem to apply more generally to systems in nature, although one doesn't quite understand why. So let's get to a specific example of non-equilibrium that that is important and that one would like to understand rigorously. And that example is the flow of heat in a collection of systems. So I take a chain of n+1 modes, 0, 1 to n, and I construct a Hamiltonian which is the sum of a Hamiltonian for the individual nodes plus interaction between consecutive nodes. And the idea is that from such a Hamiltonian, which you can take as good as possible, say a chain of geodesic flows on manifolds of negative curvature, you should be able to understand the Fourier's law, which is the law that describes the heat flow through this chain. And immediately it is found that this is a very difficult problem. In fact, Joe Leibowitz has made a lot of propaganda around the fact that this is a very hard problem. So I will tell you some things that one can do about this system, and that will maybe show you why it is a hard problem. So I assume that the Hamiltonian of the individual system corresponds to a Anosov Hamiltonian flow, namely, say, the geodesic flow on a surface of negative curvature. And then I will use a very a difficult and important result due to Liverani, that for such systems the correlation functions decay exponentially. So if you look at a collection, one such system, Hamiltonian and Anosov, the time correlation functions decay exponentially. The system forgets somehow its initial condition exponentially fast. Now I have defined some alphas there. It doesn't matter what they are precisely. And I will immediately say that the problem, as I have presented it, is beyond what one can handle at this time. So one way to simplify this problem is to introduce a thermostat. Basically, this means that at each node, instead of allowing the energy to fluctuate, you fix it at some value. Fixing the value of the kinetic energy amounts, in fact, or can be interpreted as fixing the temperature. Now, what one can do is to study this thermostated system and apply a very highly non-trivial perturbation theorem of Dolgopiat to it. So the perturbation would be the these interparticle interactions plus the thermostat, which is an extra term in the Hamiltonian. Now, why should this be a difficult problem? Well, as I told you, systems that one understands rather well are these hyperbolic systems with expansion in one direction, contraction in another one. Now, when we study chain, heat propagation through a chain of subsystems, we are in fact taking in zeroth order the product of the hyperbolic system, but each of these systems has a neutral direction, which is the direction of flow. So it is non-hyperbolic, if you like, in one direction. Since this is the direction of time evolution, you can get rid of it if you consider only one system. But if you have a collection of systems and you couple them, then you start with a perturbation. You want to perturb a system which has in fact a number of neutral directions, and that is difficult. Fortunately, there is a highly non-trivial result of Dolgopiat that allows you to handle the linear response in that case, and it gives a formula that is the expected formula. What is not obvious is that there should be a correction of the order of lambda, namely of the order of the perturbation. I mean, for those who know about this, think of the linear flow on a torus in n dimension. This is something very unstable, and it tends to have lock-in of frequencies, and near the Lebesgue measure there are all kinds of other measures that arise through perturbation, and we have in this case a theorem that allows all these measures to be handled with a uniform correction. That is quite remarkable. Now, what one does is one assumes, I mean, in what I said, the temperatures from were given arbitrarily. These corresponded to kinetic energies that were fixed at the beginning. But of course, one would like to fix them in a natural way. And the natural way is to say that the thermostats that we have introduced that the thermostats that we have introduced give no net flux of energy to the system. That determines then a sequence of temperature that satisfy Fourier's law. That's one approach that I've presented to you here. There is another approach, in fact, earlier due to Dolgopiat and Liverani, which may sound more pleasant to you for technical reasons, but which involves taking a macroscopic limit. So instead of having a discrete chain with n elements, you let this number tend to infinity. Well, for the purposes of the present discussion, I like to have a finite chain, a discrete chain. So the impression I want to give you is that treating one of the most obvious and simple problems in non-equilibrium statistical mechanics, namely the flow of heat in a chain of very well-behaved systems, that leads to problems which are a little bit beyond the limit of what one can do now. Namely, if you wanted to treat the full Hamiltonian system, nobody has been able to do it. Cheating in one way or another, and the way is slightly different in what Dolgopiat and Liverani do and what I am showing you here, one barely gets to the possibility of handling these systems. Oh, yes?
Can you explain why cheating like that makes things more simple?
Louder.
Can you explain why cheating the way the Dolgopiat and Liverani did, or the way you do, makes the problem simpler? Why does the problem is simpler when you fix the energies?
Well, when you have only one subsystem, that the problem is simple. As soon as you have a chain, it is difficult. Now, of course, if you apply blindly the linear response formula, then there's no problem. The problem is to show, in fact, that this linear, that the correction term 0 of lambda is uniformly small. And this has not been done even close to equilibrium, etc. So at this point, I'm trying to see what can be done rigorously, and the question is that we fall short of being able to handle this problem rigorously because of the one theorem that we are able to use, which is this Dolgopiat theorem, which is known only with strong limitations. Any other question at this point? Okay, so I'm trying to show you what difficulties you meet if you want to do things rigorously from a fundamental point of view. I'm quite well aware that this theory of linear response close to equilibrium gives good results and is accepted by most physicists. On the other hand, it's easy to find counterexamples with chains of harmonic oscillators harmonically coupled, which do not satisfy the normal flow of heat. And therefore, if you want to treat that situation, if you want to prove a theorem, you face a difficult question. Okay, so having seen what is more or less the most difficult, the simplest problem in non-equilibrium that one can more or less handle, let me jump ahead and go to three-dimensional fluid turbulence. And many people will say, well, this is a problem in PDEs. I want you to forget for a moment that there is such a thing as a PDE and think of a physical system. So as a physical system, it's a Hamiltonian system. If you think of incompressible inviscid fluid, to which one has to add dissipation, and the Navier-Stokes equation contains inviscid part plus a term that describes viscous dissipation. Now, physically, what one sees are localized structures which have the name of eddies, and one finds that energy goes from the large eddies where energy is in fact input to small eddies where it is dissipated by viscosity. And what happens in effect, as one sees by numerical simulation, is that vorticity forms tubes. These tubes are unstable under time evolution, and they tend to fold, and then when at the same time that they fold, they are elongated and they break up into small things of smaller diameter, and that's how one sees that the energy goes from large scales to small scales. But seeing it in simulation doesn't mean that one has a good theory. Now, there is a famous theory of turbulence, which is the Kolmogorov theory. If you assume that turbulence is isotropic and homogeneous, then features of the energy cascade can be determined by so-called dimensional arguments. Now, what is dimensional argument is a notion that is not so familiar with pure mathematicians. The quantities that one uses in physics are quantities with dimension. A velocity is not a real number, it's a number of centimeters per second. And if you take the cube, you have cubic centimeters by second to the power 3. And if you take the logarithm of that, it's nonsense, because, or the exponential of that, it's nonsense, because the exponential of the logarithm of real numbers has sense, but if you have a dimension, then the result depends of taking exponential, cosine, etc. Depends in a complicated way on the units that you use, and therefore you have to be careful about dimensions. Now, if you handle dimensions in a proper way, then you find that many quantities have a unique expression, and that determines that some quantities depend on some others, like that other to an exponent that may be 5/3 or something like this. So this is a simple consequence of some scaling properties of the equations of hydrodynamics. This is beautiful, and the Kolmogorov theory has been enormously useful. However, experimentally, turbulence is not isotropic. And if you look at a quantity, which is here, the change in velocity over distance r to the power p, this scales like r to a certain exponent zeta p, and the Kolmogorov theory tells you that this zeta p is p over 3, and experimentally one finds something else. The experiments are not very precise, but experimentalists are quite convinced that you find something else than p over 3, except for p equals 3, because the exponent for p equals 3 is zeta p equal 1. Okay, so what can we do? What I want to do is to present a physical version of hydrodynamic turbulence, which takes into account the fact that you have energy percolating from high cells to small cells, from large eddies to small eddies. So let me decompose my system into cubes, and in each cube take a finite base of divergence-free real vector fields with integral 0. Then I can hope to decompose the global velocity field, say in a cube, into small a number of wavelets. So let me interpret this as a Hamiltonian system, which is a union of collections of cubes, and in each cube you have only a finite number of degrees of freedom. So the picture is something like this: a big cube, and then you have cubes of various level, in each cube smaller cubes, etc. So I have a discrete dynamical system with interaction between different levels, and that can be interpreted as in the same way as a heat flow. So each of these cubes with a finite number of degrees of freedom would be considered as a system that interacts with cubes of lower and larger degree, and having to this collection of systems, you put energy in the large eddies, and it is dissipated in the small eddies, so you have a situation like that of a heat flow. I mean, this is unescapable, and this says that in some sense the hydrodynamics of turbulence is the same thing as a heat flow. There is a problem. We would have to believe that the various cells, large and small, that I have introduced, do interact in such a way that the interaction is relatively small, that it's not too large. This is in fact not very different from something that people in turbulence theory accept, which is called locality in k-space. So one admits that in k-space there's not too much interaction between different levels. So it is at least not totally implausible from the beginning that we can handle this system as a heat flow. Now, we can evaluate the temperature of the large eddies in this way. This is not the temperature in the usual sense. It's the temperature if we consider that the turbulent energy cascade is, in some sense, in some mathematical sense, the same thing as a heat flow. Then the Kolmogorov tells you what the kinetic energy is at a certain level. I will not explain the notation, but it has this 11/3 that comes in naturally. And having this kinetic energy, if you divide by Boltzmann's constant K, you get a temperature. And this temperature is huge because the kinetic energy is macroscopic, and K is known to be a very small number. So that means that from this point of view, if you think of the turbulent cascade as a heat flow, it goes from very high temperature to somewhat smaller temperature, and with a heat resistance that would be large, which would correspond to small coupling between the different things. So there's nothing physically wrong, nothing obviously wrong with this picture. However, what does it tell you? Well, it doesn't give you much, because all the quantities that all the quantities of interest should be determined according to Kolmogorov by dimensional arguments. And if instead of thinking of a cascade of energy through eddies of various sizes, if you think of heat flow through systems of various sizes, the answer would in both cases be given by the dimensional argument and be the same. So you've lost nothing, you've gained nothing. However, this approach has the possibility that you can look at microscopic fluctuations which are observed to be different in turbulence from those predicted by Kolmogorov. And we can think of these microscopic fluctuations as being thermal fluctuations. Now, there is a difficulty, which is that thermal fluctuations are perfectly well understood in equilibrium, but in non-equilibrium, this is a hard problem on which people like Gianni Lassigno, who was here last week, have been working. However, for the purpose of the present discussion, we can be brutal and say we think there is a local temperature. We look at fluctuations corresponding to this local temperature, corresponding to a Boltzmannian distribution. That means that we have a sequence of different scales, the ratio of one cube to the next smaller cube, and we assume that when we go from one level to the other, you have thermalized the situation, which Christian Beck hit the same idea 20 years ago and make calculations which are in some sense very close to this. Now, although with a different interpretation, in any case, this allows you to compute these so-called structure function, namely these quantities here, and one finds an expression which is this one for the exponents. This is, although it looks like a beautiful mathematical formula with a gamma function, this is a result of an approximation. However, one can believe that this approximation is not physically unreasonable, and certainly what one obtains is zeta p's that fit the experimental data, provided the kappa, the ratio of boxes of different sizes, is chosen appropriately, kappa being something like 20 or 25. Okay, so what did we gain by this? Well, there is one thing that we have gained. We have a clear reason why the energy flows from the large eddies to the small eddies. This is because energy flows from high temperature to small temperature. This might be a bit confusing to people in hydrodynamics, because in for two-dimensional hydrodynamics it is supposed to be different. However, 2 dimensions is pathological from a dynamical point of view, in a sense that it's highly non-ergodic. So this is the counterexample is not convincing. This remains a good explanation why energy goes from large to small eddies. It is an entropy effect, if you like, typical non-equilibrium effect. But there is another thing that we get, namely an estimate of this kappa. So it says that nature tells you that the ratio of sizes of the boxes should be this large number, 20 to 25. This, to me, is satisfactory. One can relate this also to the Reynolds number at the onset of turbulence. Let me not go into that. But what it says, in my opinion, is that if you take a system that is described by very simple equations, it creates a tremendous complexity corresponding to the difference between scales of the boxes, and that means that between these two, one scale and the next, there should be all this folding of vortex tubes and elongation, etc. So this is one example among many that simple problems can have complicated answers, and that we have precisely to expect that for non-equilibrium dynamics. Okay. Let me go then to the next subject, which is life. Well, life is a non-equilibrium phenomenon. It is definitely more difficult than turbulence. The reason, the technical reason, is that turbulence is given by the partial differential equations, and this is due to the fact that it's a transport phenomenon. In life, necessarily, there are chemical reactions which are much more difficult to handle. They lead to other aspects of non-equilibrium, like metastable states which play a necessary role, and so on. So life is a more difficult problem, and if we believe what the example of turbulence tells us, we do expect very complicated answers. Life, being a non-equilibrium problem, leads naturally to complicated answers, which experiment or the observation of nature supports. But that should not be then unexpected. So, sorry. So we do not expect that the theory of non-equilibrium in the poor state in which it is will tell us a lot about life. On the other hand, knowing that life is an example of non-equilibrium, it tells us something about non-equilibrium processes in general. Namely, that we should expect in non-equilibrium physics at least the complication that we see in life. Now, in putting non-equilibrium, in putting the problem of life in the framework of statistical mechanics, I'm following Schrödinger, but of course it is not equilibrium statistical mechanics, it's non-equilibrium. And the strange thing is that contrary to hydrodynamics, the energy here is injected as well as dissipated at microscopic scales. So what one should convince oneself is that that it's natural for information of microscopic origin to percolate to more macroscopic structures. This is also observed in crystal growth, but this life is different because there is a persistent metabolic activity, and one can see in detail that these two situations are different. But it does not mean that it is easy to give an abstract definition. In particular, the notion of non-equilibrium steady state that was useful in other situations does not seem to be very useful for life, because there is in life a historical development due to mutations and so on, and therefore a steady state is not a good approximation. It doesn't explain how life can originate, and it is in contradiction with the fact that life evolves with time, even if only slowly. So if this needed to be proved, life remains a difficult problem from the point of view of non-equilibrium statistical mechanics. And I'll stop there. Thank you.
Thank you very much. Very remarkable. Are there any questions or remarks or comments?
Thank you. Maybe I have a very nice question. I apologize, I'm not expert on this topic, but just to understand the contrast between the Kolmogorov treatment and like what you call the microscopic approach, where you get this correction to the exponent. So is it fair to some extent to say that the situation here is quite similar to the theory of critical phenomena, where if we start with the mean field theory, say at lambda, we get universal exponents, but we miss the thermal or quantum fluctuations. But then if we consider the renormalization group at a Wilson or Cadenon, we get the same exponent plus more corrections. I'm just wondering.
Yeah, I guess that would be a possible way of approaching the problem. So the way I have approached it is just very brutal, using these equilibrium fluctuations, but one can certainly do better. In fact, Gianni Ionalassigno said that he would look into it.
Okay, well, before we take it, Michael.
I'll just ask a question about the life bit at the end. So you have a feeling that the theory of natural selection seems to be going in the opposite direction to the idea of entropy increasing, intuitively. Would you think that's a fair comment, that you tend to, the most successful species will evolve preferentially, so you end up with a very ordered solution rather than a very disordered solution?
Well, obviously, what we observe of life is a very particular aspect. This is what remains after all these early things have killed each other. We have only one genetic code. We can go back to the notion that RNA was at the beginning, but obviously there must have been things before RNA, and an approach based on non-equilibrium statistical mechanics, to the extent that it exists, would be trying to look at things from the other end. And all that the existence of life tells us that there must be something at the other end, but we see very little of it now. But indeed, an essential part of life is the evolution. If there was no evolution, evolution must be important at the beginning of life as it is now. Simply, the evolution before there was a genetic code, etc., must have been of a rather different nature. It is the notion that if you take non-equilibrium systems, they have a tendency, or a possibility at least, to develop more complexity over larger scales, which is a non-obvious fact, that this is something that could go on. So the existence of life tells us that there is this possibility to create more structures which are not like crystals, because they are changing structures using the influx of negentropy, and that this can go on, that there's no natural limit to the complication of structures that can be obtained. So that's a remarkable fact that the existence of life tells us.
A remarkable aspect of life, which is probably not so easy to formalize in just a physical description, is the fact that, of course, life changes continuously in life. So there is something more. So we are not setting boundary conditions. Things are self-consistent, and evolution is about somehow going, a path of joint coupled evolution. So I guess that's what there is. Something more that is related to the fact that changing organisms change the way they use energy, and they change the way how efficient they are, and they change the atmosphere, they change the biosphere. So this is, I think that the paradigm of looking at life probably requires something more than just a physical point of view.
one can imagine that with some energy influx from light or chemical, you create molecules of a certain complexity. But that this would go on
Yes.
is a surprise. Yeah.
About your turbulent, your discussion about turbulent flows.
Yeah.
I mean, what people in turbulence call locality in Fourier space is, with your analogy, it is more like locality of the interaction.
Yeah, it is locality of the interaction. So what I would need locality of the interaction, not using Fourier space, but using the space of labels of these wavelets,
Right.
which is not so different.
You can have locality of interaction without having weak coupling. It seems
Without having...
without having weak coupling between these two things seems different.
Well, the notion, well, I mean, of course, nearest neighbors can have strong couplings, but if you go beyond a certain size, the coupling should decay. And what I'm asking here is that one is capable of taking a size, which I said 20 or 25, such that you really have weak coupling in some sense.
This is a very difficult thing, very difficult an idea which is very difficult to formulate.
That is of course a strong assumption. Now these calculations which Christian Beck made for the velocity distribution seem to be in agreement with something like that.
You've presented quite a journey from rather simple, smooth dynamical systems over models for turbulence and now to discussing aspects of life. I'm wondering whether you have any more precise ideas about, say, the mathematical models that might be capable of describing life in a more proper sense, or some conditions that you would expect you have to put in order to come to some more mathematical.
I think there is a big difficulty, which is the fact that there are chemical reactions. Now, there is no impossibility to describe molecules by ordinary differential equation. However, in life, certainly, the metastability, the fact that most molecules that form life are in fact metastable, creates a different situation, which is somewhat difficult to describe in a natural way. So the model of differentiable dynamics in low dimension, I see how it can extend to systems like perhaps hydrodynamics. How it would handle the chemical reactions in life is less obvious.
I might remark that it seems there's a kind of current trend at the moment that quite some biological systems are described by stochastic models that are strongly correlated, and in that way reproduce dynamics that is not Brownian but more correlated in a sense that indeed, which corresponds to another remark of you, that there are no non-equilibrium steady states, that they also exhibit aging properties and very slow relaxation properties.
Okay.
Would that go in this direction?
I have nothing against stochastic models as an approximation to real dynamics, but if anything that you extract from stochastic dynamics that does not come from deterministic dynamics, I would be quite skeptical about.
Thank you.
Now, one Rothschild professor will ask another Rothschild professor a question. Alexandra.
Do you think it is possible to describe life without quantum mechanics?
Without?
Without quantum physics, quantum mechanics?
Well,
I think it.
I mean, the consensus is that beyond a certain size, which is actually quite modest, classical mechanics gives a good description of things. Of course, you cannot compute the hydrogen energy levels, but see, the simplification that you get in your thinking by saying that the system is classical is worth taking, in my opinion, until you find something where the quantum aspect would make a serious difference. I mean, one simplification that occurs is that in classical mechanics with a Hamiltonian that contains a p squared over 2m, you have the temperature immediately. While in quantum mechanics, the temperature occurs in a more complicated way. You cannot simply take the kinetic energy and get the temperature. So I have nothing against quantum mechanics, but I take the simplest situation that seems to be needed for the study.
Okay, I suggest that you carry the conversation off out into the hall where there's some wine and nibbles waiting for you all. Let us thank once again David Ruelle for a wonderful lecture.